Welcome to the Deep Dive. Today we're focusing on, well, a really vital question as our roads get more crowded. Can artificial intelligence in cars actually make streets safer for pedestrians?
It's a huge issue, especially when you look at the numbers.
Exactly. I mean, despite all the advances in vehicle safety over the years, pedestrian fatalities in the U.S., they actually jumped, what was it, 37% between 2000 and 2020?
Yeah, a really concerning trend. And in 2020, pedestrians accounted for 17% of all traffic deaths.
Wow.
That's significant.
It really is. And, when a vehicle hits a pedestrian, the outcome is often just devastating.
Absolutely.
So this deep dive into how AI is trying to tackle this improved pedestrian safety is brought to you by the Be Safe, Be Seen podcast. We're sponsored by Reflectos, the high-visibility cycling and running gear brand.
And that rise in fatalities, it just underscores the need, doesn't it? We need better ways to protect people on foot. We've done a lot for car occupants, but these stats show we need a wider focus.
Yeah, and AI is really being presented as the solution, or at least a big part of it.
Right. For ADAS advanced driver assistance systems and, eventually for fully autonomous vehicles.
The idea being that AI can give cars better perception, faster reactions, maybe even better than us humans sometimes.
That's the promise. And that's exactly what we want to dig into today. What's our mission here is to figure out, okay, are these AI systems creating genuinely smarter cars? And more importantly, does that actually mean demonstrably safer streets for pedestrians?
Right. It's not just about cool tech.
No. We need to see real safety benefits, real-world outcomes, not just fancy algorithms.
Absolutely. We need to get past the hype, look at what these systems can really do, what their limits are, and what impact they're actually having. This is about people's lives.
Exactly.
So let's start at the beginning. What are the core AI technologies that are supposed to make these smarter cars work?
Okay, so the foundation really rests on giving cars better ways to perceive and then decide. It starts with computer vision.
Giving the car eyes.
Essentially, yeah. Using cameras and other sensors to interpret the visual world, identify pedestrians, cars, lanes, that kind of thing. Learning to see what's relevant.
Okay, so it sees things.
Mm.
But just seeing isn't enough to stop an accident, is it? That's where machine learning fits in.
Precisely. Machine learning, or ML, that's the learning part. These algorithms get trained on, massive amounts of driving data.
Okay.
And through that data, they learn to recognize patterns, get better at spotting pedestrians in all sorts of situations, different lighting, weather, crowded streets. They improve over time.
And I keep hearing about deep learning being the real game changer here. How's that different from traditional ML?
Right. Deep learning, DL, it's a subset of ML, and it's really fueled the recent breakthroughs. With older ML, engineers often had to manually define the features the system should look for, like the shape of a head and shoulders,
Ah, okay. Handcrafted features.
Exactly. Deep learning models, especially these things called neural networks, they can learn these important features automatically, directly from the raw sensor data, like images.
So the AI figures out the best way to identify a pedestrian itself, just from the data.
Pretty much. It learns the critical patterns, which often leads to much higher accuracy, especially in complex scenes.
And convolutional neural networks, CNNs, they're sort of the workhorse for images in this.
Yes, CNNs are incredibly good at processing image data. They learn to pick up on textures, shapes, patterns, all the visual cues that help distinguish a pedestrian from, say, a lamppost or a shadow. They're really central to modern visual perception systems.
Got it. There are older methods too, right? Like SVM.
Oh, yeah, definitely. Traditional algorithms like k-nearest neighbors, support vector machines, SVM, they were used often with those handcrafted features or data from sensors like LiDAR. There was a study using 3D LiDAR data and SVM that got pretty decent results, like 81% sensitivity.
But deep learning sort of took over.
Largely, yes, for perception tasks, especially with things like region-based CNNs or RCNNs, which are very accurate but maybe a bit slower. Yeah, they have a two-stage process. First, find regions of interest, then classify them. But then you have models like YOLO. You only look once.
Catchy name.
It is. And it's fast. It does detection and classification in a single pass, making it great for real-time applications in cars. YOLO 3, for example, uses a specific architecture, DarkNet 53, and predicts at multiple scales to catch pedestrians of different sizes.
Okay, so speed versus accuracy trade-offs sometimes.
A bit, yeah. Though YOLO's gotten very accurate, too. There's research optimizing models like YOLO for running efficiently right on the car's hardware, what we call edge devices. Getting decent speed and accuracy, like maybe 78% accuracy at a few frames per second.
But this shift to deep learning, While powerful, it also makes things more complex, maybe harder to understand why the AI made a certain decision. The black box problem.
That's a huge point. These DL models can be incredibly complex, millions of parameters. Understanding their internal reasoning is tough. That's why there's a growing field called explainable AI, or XAI, trying to make these decisions more transparent.
Right, and you mentioned training data earlier. The quality of that data must be critical.
Absolutely crucial. Deep learning models are data hungry, and if the training data isn't diverse and representative of the real world, the system can develop biases.
Biases like what?
Like performing better at detecting certain types of pedestrians than others, maybe based on demographics or even clothing, simply because the training data skewed that way. That leads to real concerns about equitable safety.
Okay, so computer vision, machine learning, deep learning, these are the brains. But you said cars use more than just cameras for their eyes. Let's talk about the sensors.
Right. Robust perception needs multiple sensor types working together. Sensor fusion is key.
So cameras we covered, rich visual detail, color, texture. What about LiDAR?
LiDAR, light detection and ranging. It uses laser pulses. Think of it like radar, but with light. It creates a very precise 3D point cloud, like a digital map of the surroundings.
What's the advantage?
Excellent for measuring distance very accurately and determining the precise shape of objects. This really helps distinguish a pedestrian from, say, a signpost or a bush, especially in 3D space. And ML techniques are used on this LiDAR data too, not just images.
Okay. And radar. We know it from speed traps, but how does it help here?
Radar uses radio waves. It's great for detecting range, speed, and the angle of objects. It's a big advantage. It works really well in bad weather rain, fog, snow, where cameras and even LiDAR can struggle.
So it's more robust in poor conditions.
Exactly. And newer radar systems are getting much better at detecting stationary objects too, not just moving ones. So a pedestrian standing still is more likely to be picked up.
Interesting. Are there others, like thermal imaging?
Yes, thermal or infrared cameras. They detect heat signatures. This makes them incredibly valuable in low light or nighttime conditions, or when visibility is obscured by fog or smoke.
And nighttime is when most pedestrian fatalities happen, right?
It is. NHTSA has really emphasized the need for better pedestrian AEB performance in darkness, and thermal imaging is seen as a key technology to achieve that.
So you have all these different sensors cameras, LiDAR, radar, thermal, each with strengths and weaknesses. How does the car make sense of it all, that sensor fusion?
Exactly. Sensor fusion is where the AI algorithms combine the data streams from these multiple sensors. The goal is to create a single, unified understanding of the environment that's more accurate, more reliable, and more complete than any single sensor could provide alone.
So it's like getting multiple opinions.
Kind of. It helps fill in the gaps. LiDAR might struggle in heavy rain, but radar might still work well. Cameras might be blinded by sun glare, but LiDAR might not be affected. Fusion provides redundancy and a more robust perception overall, minimizing blind spots.
Sounds powerful, but also complex to get right.
Oh, definitely. Sensor fusion is challenging. You need to make sure the data is correctly aligned in time and space, handle conflicting information from different sensors, ensure the sensors are properly calibrated. If the fusion algorithm isn't sophisticated enough, it can sometimes lead to errors.
And there's debate about the best approach.
Right.
Like Tesla relying heavily on cameras versus others using a multi-sensor suite.
Yes, that's an ongoing discussion. Tesla's vision-only approach is quite different from most other automakers who integrate LiDAR and radar alongside cameras. Each approach has its proponents and potential trade-offs.
Okay, so we have the sensors gathering data, the AI algorithms processing it through fusion. How does this all add up to the car actually understanding its surroundings better, having better situational awareness?
Well, it enables several key capabilities. First is object detection and classification. The AI analyzes the fused sensor data in real time to not only detect objects but also classify them: pedestrian, car, cyclist, etc. It figures out their size, shape, position, and importantly, their trajectory where they're moving.
So not just something is there, but that's a pedestrian and they're moving towards the road.
Exactly. And the next level, which is really advancing now, is behavior prediction.
Predicting what the pedestrian will do next.
Yes, AI models are being trained to analyze movement patterns, look at historical data for similar situations, consider contexts like crosswalks or bus stops, and predict the probability of future actions. Will that person step off the curb? Are they likely to cross?
Wow, that sounds incredibly difficult, but potentially very powerful for avoiding accidents.
It is. And all this feeds into real-time decision-making. Based on the classified objects, their predicted behavior, and the overall scene understanding, the AI system has to make very quick decisions.
Like warning the driver or hitting the brakes.
Precisely. It could be an audible or visual alert, or if the system determines a collision is imminent and the driver isn't reacting, it can trigger autonomous emergency braking, or P-AEB.
And these AI models, like the YOLO versions you mentioned, they're constantly evolving.
Yes, there's continuous development, newer versions offer better performance, but that rapid evolution also presents challenges for standardization and regulation, making sure systems meet consistent safety levels.
Okay, so that's the tech background. How is this actually showing up in cars we can buy or that are being tested on roads now? What are these smarter car features?
We're seeing these AI capabilities translate into specific features in ADs and developing autonomous driving systems, or ADS. The most common are things like real-time pedestrian detection with driver alerts.
The warnings.
Yes. And crucially, pedestrian automatic emergency braking, P-AEB, which we've mentioned, that's becoming increasingly standard.
What else?
Enhanced situational awareness tools like 360-degree camera views on the dashboard, sometimes highlighting detected pedestrians, and then more advanced stuff is emerging. Cloud analytics for fleet safety, sometimes remote camera access, automatic creep speed in pedestrian zones, even experimental things like visual communication signals from the car to pedestrians.
A digital thumbs up.
Yeah, things like that are being explored. But it's important to remember, as you hinted earlier, there's no single definition of a pedestrian detection system.
Meaning the capabilities vary a lot.
Hugely. Different sensors, different software, different levels of integration. This creates a potential expectation gap. For drivers, they might assume the system can handle everything, which isn't the case.
Can we look at some specific examples? How are different manufacturers implementing this?
Sure. Take Tesla's Autopilot, or full self-driving beta. They famously use a primarily vision-based approach, relying heavily on cameras and sophisticated neural networks trained on vast amounts of real-world driving data. They include collision avoidance and emergency braking for pedestrians.
But they've acknowledged limitations too, right?
Yes, particularly with detecting objects accurately at higher speeds or in very complex, cluttered scenes. Then you have Volvo, pioneers in safety. Their city safety system uses both cameras and radar.
Okay, multi-sensor.
Right. It's designed to detect pedestrians, cyclists, even large animals, providing warnings and AEB. But they're clear about limitations too. Performance can be affected by strong sunlight, temperature extremes, sensor obstructions, and importantly, they state the P-AEB function is deactivated above 80 kilometers per hour, about 50 mph.
That speed limitation seems common. What about Subaru?
Subaru's eyesight system is well known. It uses stereo cameras, 2 cameras spaced apart, which gives it depth perception, like human eyes, helping judge distance and recognize objects in 3D, including pedestrians. It features pre-collision braking.
And limitations.
They note performance is affected by adverse weather, and their pedestrian detection for braking typically works at closing speeds below about 19 mph.
19? That's quite low. Toyota.
Toyota Safety Sense, TSS, also typically uses camera and radar. Their pre-collision system, PCS, includes pedestrian detection, offering warnings and auto braking, generally within a speed range of roughly 7 to 50 mph. Newer versions are adding capabilities like support at intersections and detecting motorcyclists.
So improvements are ongoing. Ford, Mercedes.
Ford's Co-Pilot 360 includes pre-collision assist with AEB, using sensors to scan ahead for potential collisions with vehicles or pedestrians. Mercedes-Benz has active brake assist with pedestrian detection, and they're also heavily investing in AI for manufacturing and developing higher levels of automation like their Drive Pilot system.
What this highlights is that every manufacturer states limitations, these operational design domains or ODDs. Smarter doesn't mean infallible or all capable.
Absolutely critical point. These systems are designed to work under specific conditions. Driver education about what the system can and cannot do is paramount. Over-reliance is dangerous.
And it's not just the car brands, right? There are key tech companies behind the scenes supplying these systems.
Definitely. Companies like Mobileye are huge players. They specialize in vision-based ADS. Their IQ chips are in millions of vehicles. They offer pedestrian collision warnings, often triggering alerts when the time to collision, or TTC, is less than 2 seconds. Their newer systems offer 360-degree perception.
2 seconds isn't much time.
It's not, highlighting the need for quick system reaction or driver intervention. Then you have Nvidia with their G-Drive platform, powerful hardware like the Giraffe Orin chip, and comprehensive software stacks for perception, fusion, planning. They lean heavily on AI and simulation for development.
Okay.
Others? Bosch is another major supplier, providing ADS components and even vehicle computers, using deep learning for things like predicting pedestrian behavior. They also work on active safety, like hoods that pop up slightly in a pedestrian collision to cushion the impact. Continental is also involved, working on pedestrian protection, radar systems, and fusion.
So it's a really complex ecosystem, this supply chain.
Yeah.
Makes you wonder about accountability when things go wrong.
That's a whole other can of worms we should get into later. But yes, integration and accountability are complex.
Okay, so we have smarter cars with these impressive, albeit limited, capabilities. Now for the big question. Are they actually leading to safer streets? What's the evidence on accident reduction?
This is where we need to look hard at the data. And the picture is, well, promising but complex.
Let's start with the positive signs. What do studies show?
Okay, NHTSA and IHSS have done significant research. The PARTS study, a collaboration, found that P-AEB systems led to a 9% reduction in reported crashes involving non-motorists, so pedestrians and cyclists.
9%, okay.
And separate IIHS research suggests that automatic braking, specifically designed to recognize pedestrians, could cut those types of crashes by about 27%.
27% potential, that's a bigger number.
It is. And the Highway Loss Data Institute, HLDI, looking at insurance claims for Subaru eyesight vehicles, found somewhere between a 35% and 41% reduction in claims likely related to pedestrian incidents.
Wow, insurance data showing a big drop.
Yeah, and another study by the U.S. DOT's Volpe Center estimated that widespread adoption of pedestrian crash avoidance and mitigation systems, PM, could potentially prevent around 5,000 crashes and maybe 810 fatalities annually in the U.S.
So there's definitely evidence that these systems are helping reduce collisions.
Yes, the trend seems positive. However, there are caveats. Well, other analyses looking at insurance data showed a pretty wide range of effectiveness, maybe 18% to 57% reduction depending on the study and system. And some studies looking at police-reported crash data didn't find statistically significant reductions, maybe only around 4%.
So inconsistency in the findings.
Yeah, and one review looking specifically at AEB for vulnerable road users found roughly a 20% reduction in crash risk, give or take 10%, but importantly, they couldn't verify any significant reduction in injury severity when crashes still happen.
So maybe good at avoiding lower speed bumps, but less proven for reducing harm in more severe impacts.
That seems to be the implication from some studies. The main benefit appears to be crash avoidance rather than injury mitigation in unavoidable crashes right now. And remember that IIHS estimate. If systems were perfect, maybe 65% mitigation potential. The fact we're seeing figures like 9% or 27% in reality shows there's a gap.
And that gap is likely due to real-world conditions.
Exactly. Test track performance doesn't always translate perfectly.
Let's talk about those conditions. We touched on lighting. How bad is the nighttime problem?
It's arguably the biggest challenge right now. As we said, multiple studies showed degraded performance in low light. That AAA study calling P-AEB nearly ineffective at night is pretty damning.
And 72% of pedestrian deaths happen at night, according to NHTSA.
Right, so the systems struggle most when the risk is highest. That's why there's such a regulatory and research push for better nighttime performance, often pointing towards thermal imaging as a necessary addition. One study on a thermal system showed really high accuracy, like 92–94%, though even that noted potential issues like umbrellas blocking the heat signature.
And it's not just darkness, right? Bright sunlight.
Yep, strong sunlight, glare, reflections off wet roads, those can overwhelm cameras and even affect LiDAR sometimes.
What about bad weather? Rain, snow, fog?
Big impact, especially on cameras and LiDAR, which rely on clear sight lines. Heavy rain can significantly cut LiDAR's range, maybe by half. We know AI model performance drops in simulated weather. Radar and thermal tend to be more robust, but not immune.
Okay, and complex city environments.
Very challenging. Crowded intersections, people jaywalking unpredictably, cyclists weaving through traffic, visual clutter everywhere. It's hard for AI to process reliably. High pedestrian density can strain some systems. Plus, urban canyons' tall buildings can block GPS and cause radar-LiDAR interference.
And vehicle speed, we mentioned those operational limits.
Yes, efficacy drops off or systems deactivate at higher speeds. Remember Volvo cutting off P-AEB at 50 mph, Toyota's 750 mph range? And HTSA aims for P-AED to reduce impact speeds to below 25 mph for their head protection standard. but many fatal crashes happen faster than that.
So hitting a pedestrian at 40 miles per hour might still be fatal, even if AEB activated.
It might reduce the impact speed, which is good, but maybe not enough to prevent serious injury or death, especially if the initial speed was high. One study even found AEB helped more for bicycles than pedestrians on high-speed roads.
So the focus really has to be on improving performance in these tough conditions, especially darkness.
Absolutely. That's where the regulations are heading and where a lot of R&D, particularly into thermal and more robust AI, is focused.
What about other limitations of current systems we see on the road?
Well, there's inconsistency across different makes and models. Early systems were often primarily designed for vehicle-to-vehicle rear-end crashes, and adapting them seamlessly to pedestrians who can approach from the side or move erratically is harder.
Detecting children.
That's another challenge: smaller size, sometimes faster, less predictable movements. Sensor obstruction is a practical issue too. Dirt, snow, even a bike rack can block a sensor, sometimes disabling the system without a clear warning.
And the pedestrian often has no idea if the car has even seen them, right?
Exactly. There's a lack of feedback to the person outside the car. So overall, while progress is being made, particularly in avoiding some crashes, the evidence on significantly mitigating injury severity in those crashes that still occur is less conclusive. Future work might need to focus more on intelligent impact mitigation, integrating ADOs with passive safety systems.
Okay, that gives us a clearer picture of the effectiveness and its limits.
Yeah.
Let's pivot to some of the key underlying challenges that developers are wrestling with. What makes this so hard?
There are several major hurdles. Accuracy and reliability in complex scenarios is a big one.
Like what specifically?
Occlusion is a classic problem. When a pedestrian is partially or fully hidden behind another vehicle, a parked car, a bus.
If the system can't see them.
Right, or sees only a part, making identification difficult. There's research using newer AI like vision transformers, VITs, trying to infer the hidden parts, but it's tough. Clutter is another, just picking out a person from a busy background with lots of movement, signs, shadows.
Small object detection, like a pedestrian far away.
Yes. Fewer pixels make it harder for the algorithm. Models like YOLO 3 try to address this with a multi-scale detection, but it remains a challenge, especially with lower resolution sensors or at distance.
Then there's the issue of mistakes, false positives, and false negatives.
Hugely important. A false positive is when the system sees a pedestrian that isn't there. Maybe a shadow, a plastic bag blowing across the road and brakes suddenly.
That could cause a rear-end collision, or just really annoy the driver and erode trust in the system.
Exactly. And a false negative is the opposite, and potentially much worse. The system fails to detect a pedestrian who is there.
Leading directly to a collision the system was supposed to prevent.
Mm-hmm.
Wasn't that implicated in the Uber self-driving fatality?
Yes, reports suggested the system struggled to correctly classify the pedestrian pushing a bicycle, contributing to the failure to brake in time. It's a tragic example of the consequences of misclassification or misdetection.
And there's a trade-off here, isn't there? Tuning the system to avoid missing pedestrians might make it trigger more false alarms.
That's the precision recall trade-off, exactly. High recall means minimizing false negative, missed pedestrians, but often comes at the cost of lower precision, more false positives. Finding the right balance is critical and requires smarter AI that better understands context.
Another really concerning challenge is algorithmic bias, the idea that these systems might not protect everyone equally.
Yes, this is a serious ethical and technical issue. Studies have found disparities in detection accuracy based on demographics. Age, for one. Some research indicated lower detection rates for children compared to adults, potentially a difference of almost 20% in one study. And skin tone is another major concern.
How so?
Multiple studies, including one from Georgia Tech, found that systems were less accurate at detecting pedestrians with darker skin tones. The Georgia Tech study suggested about a 5% lower likelihood of detection, while other research has indicated disparities potentially greater than 7.5%.
Why would that happen?
It largely comes down to the training data. If the data sets used to train the AI lack diversity, fewer images of children, or a disproportionate number of images featuring people with lighter skin, the AI simply doesn't learn to recognize underrepresented groups as effectively. It learns what it sees most often.
And conditions can make it worse.
Yes, the bias against darker skin tones can be exacerbated in low light or low contrast conditions. Even clothing can play a role, ironically. Some research by IIHS suggested that highly reflective clothing, designed to make people more visible to humans, might actually reduce detection effectiveness for some AI systems.
That's counterintuitive. This has huge ethical implications, doesn't it? Unequal safety based on who you are.
Absolutely. It demands careful curation of diverse and balanced training data sets, rigorous testing for bias across different groups and conditions, and regulatory scrutiny to ensure equitable protection.
And then there's the ultimate wild card, unpredictable human behavior.
Right. Pedestrians don't always follow the rules. People jaywalk, dash out unexpectedly, change their minds mid-crossing.
The things that are hard for current AI to predict.
Very hard. Interpreting subtle human intent, is that person looking at their phone distracted, or are they about to step out, is incredibly challenging for machines that primarily rely on pattern recognition from sensor data.
How are researchers trying to tackle this unpredictability?
There's a lot of work going into more sophisticated deep learning models trained on diverse behavioral data. Predictive AI using historical patterns and real-time cues is key. Some approaches involve things like social force models, which try to model interactions, or complex planning algorithms like POMDPs or reinforcement learning. There are even things like neural social physics fields models.
That's complex.
It is. But ultimately, there might be fundamental limits to how well current data-driven AI can handle truly novel situations, those black swan events that fall outside the training distribution. Some argue we need AI that incorporates more robust reasoning, perhaps combining pattern recognition with symbolic AI or common sense knowledge bases.
Okay, these challenges lead us directly into some heavy ethical dilemmas and broader societal questions. Let's start with accidents. If an AI system fails, who's responsible?
That is a massive question with no easy answers right now. You have this complex web. The car manufacturer, the company that developed the AI software, the sensor providers, the company that integrated it all, the vehicle owner-operator, potentially even maintenance providers.
A lot of potential parties.
Exactly. And the fact that the AI itself is making or contributing to decisions complicates traditional legal frameworks based on human fault, negligence, or intent. How do you assign blame to an algorithm?
Investigating must be incredibly complex, too.
Hugely. It requires digital forensics, analyzing software logs, sensor data, maybe even the AI's training data needing expertise in both AI and automotive systems. Legal frameworks are still evolving, relying on existing product liability laws, negligence principles, but also developing new AI-specific regulations like the EU AI Act. This uncertainty could potentially slow down adoption or create insurance challenges.
Then there's data privacy. These cars are packed with sensors constantly watching the world outside.
Yes, they're essentially data centers on wheels, collecting vast amounts of information, images, video feeds, location data, movement patterns of people outside the car.
And the concern is
Concerns about unauthorized access, how long the data is kept, how it's used or shared. Could it be repurposed for surveillance by governments or companies? Could it be used for commercial profiling without consent? Pedestrians are often being monitored without any knowledge or ability to opt out.
plus cybersecurity risks, hacking that data.
Absolutely. Data breaches could expose sensitive information about people's movements and locations. Efforts are being made to mitigate this concepts like privacy by design, trying to minimize data collection, process data on the vehicle itself, edge computing, anonymization techniques, encryption, and regulations like GDPR in Europe or CCPA in California are trying to provide some safeguards.
This brings us to the infamous trolley problem scenario in the context of AI cars.
Right. The hypothetical, thankfully rare, situation where an accident is unavoidable and the AI might have to effectively choose who or what to hit, swerve into a pedestrian to avoid hitting a group, prioritize the occupants over those outside.
Do companies actually program for this?
Most shy away from explicitly programming trolley problem solutions. They talk about minimizing overall harm or focusing on preventing the situation in the first place. Nuro, the autonomous delivery company, has stated their vehicles are designed to prioritize the safety of humans outside the vehicle over the vehicle itself and its contents. But the very possibility raises profound questions.
Because ethical rules are being embedded in code.
Yes, someone, somewhere, is making decisions about how the car should behave in extreme circumstances. Who decides those rules? Based on what values? Are they transparent? What if different cultures have different ethical priorities? It potentially shifts moral decision-making from the driver in the moment to engineers and ethicists years earlier.
And those pre-programmed ethics could reflect biases too.
Potentially, yes. Decisions about how to value different outcomes or lives lack universal agreement. This highlights the need for public discussion and what some call algorithmic ethics governance.
Beyond these specific dilemmas, what are the broader societal impacts we should consider?
There's the potential impact on driver behavior and skills. Over-reliance on ADAS features might lead to driver complacency, reduced vigilance, and maybe even a degradation of driving skills over time.
The automation complacency issue.
Exactly. There are also concerns about potential chilling effects on public life if people feel constantly monitored by vehicles, potentially leading to self-censorship or reduced freedom in public spaces. And fundamentally, public trust is crucial.
Easily lost if systems fail, show bias, or if privacy is breached.
Precisely. Building and maintaining that trust through transparency, proven reliability, fairness, and clear communication about capabilities and limitations is essential for widespread adoption and realizing the safety benefits.
Okay, given all these challenges and ethical considerations, what's being done on the regulatory front? Are there standards emerging to ensure these systems are safe and effective?
Yes, regulatory frameworks and safety standards are definitely evolving, both globally and at the industry level. It's a complex landscape, but progress is being made.
Let's start with governments. What are key bodies like NHTSA in the U.S. doing?
NHTSA has been quite active. They recently finalized a new Federal Motor Vehicle Safety Standard, FMVSS number 127. This mandates automatic emergency braking, including both daytime and nighttime P-AEB on all new light vehicles by September 2029.
Mandating it, that's significant.
It is, and it comes with specific performance requirements, like being able to automatically brake for a pedestrian target at speeds up to 45 mph under certain test conditions, and avoiding a lead vehicle up to 62 mph. They're also enhancing their NCAP safety ratings program, incorporating pedestrian crashworthiness testing, largely adopting Euro NCAP methods. And there's another proposed standard, FMVSS 228, focused on pedestrian head protection during impact, setting limits for head injury criteria at speeds up to 25 mph.
What about Europe? Euro NCAP seems very influential.
Extremely influential. Euro NCAP's testing protocols and star ratings heavily drive manufacturer priorities. They have rigorous tests for pedestrian protection, both passive, how the car's front end performs in an impact using head and leg form impactors, and active, testing the performance of AEB systems, including P-AEB in various scenarios. It's expected that future 5-star ratings will likely require more advanced surround sensing capabilities.
Are there international efforts too?
Yes, the United Nations Economic Commission for Europe, UNES, specifically its World Forum for Harmonization of Vehicle Regulations, WP.29, develops international standards called UN regulations. There are regulations covering AEBS for heavy vehicles, number 131, and cars light commercial vehicles, number 152. A key UN regulation for car AEBS was agreed upon by many countries back in 2019.
And is this being mandated?
Yes. The EU, for example, mandated AEBS systems based on these UN regulations for all new models of cars from May 2022, and it applies to all new vehicles sold from May 2024. Other regions are following suit. Japan mandated auto braking, including pedestrian detection, from 2021, and Australia is considering mandates too.
So a growing global push for standardizing and mandating these core safety systems. What about industry standards? Things manufacturers use internally.
There are several crucial ones. ISO 26262 is the foundational standard for functional safety in automotive electrical and electronic systems. It provides a framework for identifying and mitigating risks due to system malfunctions.
Malfunctions. But what about systems that work as designed but still have limitations, like a sensor being blinded by the sun?
That's where ISO 21448 comes in. It's known as SOTIF, Safety of the Intended Functionality. It specifically addresses safety risks that can arise even when there's no malfunction due to limitations in the system's capabilities or performance, exactly like sensor limitations or AI perception errors. SOTIF is critical for validating AI-based perception systems.
Okay, so standards for malfunction and for intended function limitations. Anything specific to AI itself?
Yes, very recently, ISOPA's 8800.2 was published. It specifically addresses safety and artificial intelligence for automotive applications, building on 26262 and 24448. It covers the entire AI lifecycle, data considerations, dealing with the statistical nature of ML, safety analysis for AI components, and post-deployment monitoring. There are also broader ISO AS standards emerging on AI trustworthiness, bias, data quality, etc.
Seems like a lot of work is going into creating frameworks. How are these systems actually tested and validated? It must be incredibly complex.
It is incredibly complex and requires rigorous testing throughout the development process. Because these systems make real-time decisions in dynamic environments, validation is paramount.
How do they do it? You can't just test every possible scenario on real roads.
No, you can't. Simulation-based testing is absolutely essential. Companies use sophisticated simulators to create virtual environments and test the AI against millions or even billions of virtual miles, covering a vast range of traffic scenarios, weather conditions, lighting, and rare edge cases. This can be done safely and repeatably. Companies like Nvidia rely heavily on simulation.
But simulation isn't the real world.
Exactly. Simulation fidelity is a challenge, so it's combined with physical testing. This often involves using soft targets, pedestrian dummies, mock-ups of cars on closed test tracks. This allows evaluation of the system's performance in controlled, repeatable physical scenarios without risking harm to real people or vehicles.
And real-world driving.
Yes, validation also involves testing against real-world data collected from fleets and conducting carefully planned scenario-based testing within the system's defined operational design domain, ODD. Techniques like data augmentation and balancing are used to ensure the test data is comprehensive.
Are the test procedures standardized, like the Euro NCAP ones you mentioned?
Yes, standardized test procedures like those from Euro NCAP for pedestrian AEB, testing specific scenarios like an adult crossing, a child running out from behind a car at different speeds, are very influential and provide benchmarks for system performance. There are also software and system-level verification tools used earlier in development, like static code analysis, to catch defects.
So it's a multi-layered approach.
Yeah.
Simulation, track testing, real-world data, standardized protocols.
Precisely. A robust verification and validation (V&V) strategy combines all these elements to build confidence in the system's safety before it reaches the public.
Okay, looking ahead now, what are the future trends and innovations we can expect in AI for pedestrian safety? Where is the technology heading?
There are several exciting directions. One is definitely advanced sensor fusion and multimodal learning.
Going beyond just merging sensor data.
Yes. Instead of just basic fusion, the AI itself learns how to optimally integrate information from different sensors at different levels, potentially weighting inputs based on conditions to create a truly holistic understanding. Combining the strengths of cameras, LiDAR, and radar even more intelligently. Research like CRFNet explores this. Handling conflicting data between sensors remains a challenge, though.
We also talked about predicting pedestrian behavior. Is that getting more sophisticated?
That's a major focus. AI is getting better at analyzing subtle cues, body language, gaze direction, walking speed, proximity to crosswalks to anticipate intent. Researchers are using things like social force models, POMDPs, reinforcement learning, those NSRFM models we mentioned, to explicitly model the interaction dynamics between autonomous vehicles and pedestrians.
Trying to make the AI more socially aware?
In a sense, yes. And also developing AI that's more robust to sudden changes and truly unpredictable actions, things maybe not seen in the training data. This requires better generalization and maybe more abstract reasoning capabilities.
What about communication? Getting information from beyond the car's own sensors.
That's vehicle to everything, or V2X, communication. This is a huge area. It allows vehicles to exchange information directly with other vehicles, V2V, with infrastructure like traffic lights, V2I, potentially with pedestrian smartphones, V2P, and with the wider network, V2N.
How does V2P help?
A pedestrian's phone could potentially broadcast their location, or roadside infrastructure could detect a pedestrian hidden around a corner and alert oncoming vehicles via V2I. This overcomes line-of-sight limitations of onboard sensors.
So V2X complements the car's own AI perception.
Exactly. It provides another layer of awareness, making decision-making potentially much more robust and informed.
Are there new sensor technologies emerging too?
Yes. We already mentioned the increasing importance of thermal imaging for nighttime performance, driven partly by those new regulations like FMVSS 127. AI software specialized for classifying thermal images is key here.
Anything else?
Neuromorphic sensing and computing is interesting. These are event-based cameras inspired by the human eye. They only report changes in pixels, offering very high speed, low latency, and low power consumption, potentially great for detecting fast movements. Paired with spiking neural networks, CNNs, it's a different paradigm. There are research datasets like NU-AIR for this now.
And within AI models themselves, beyond CNNs.
Vision transformers, or VITs, are gaining traction. They use a mechanism called self-attention to better understand the global context of a scene, which can be helpful for things like handling occlusion. We're seeing hybrid models combining the strengths of CNNs and VITs too.
What about processing all this complex AI on the car itself and understanding it?
That brings us to Edge AI and Explainable AI, XAI. Edge AI, or edge computing, means doing the processing directly on the vehicle's hardware. This minimizes latency crucial for real-time braking decisions, reduces reliance on network connectivity, and can help with privacy by keeping data local. Efficient models like YOLO are optimized for edge devices.
And XAI, making the black box understandable.
Exactly. Explainable AI aims to make the AI's decisions transparent. Why did it detect that pedestrian? Why did it miss that one? This is vital for debugging, finding biases, validation, regulatory compliance, and accident investigation. Techniques like attention maps can show which parts of an image the AI focused on. The challenge is balancing performance with interpretability and creating explanations useful for different people, engineers, regulators, drivers.
And finally, better data is always needed, right?
Always. There's a constant need for novel datasets and benchmarks. Existing datasets often have limitations in terms of scene diversity, pedestrian appearance and behavior variations, geographic locations, or challenging conditions.
So researchers are creating new ones.
Yes, specialized datasets are emerging like the CAIS dataset for low-light conditions, UAV-based datasets like NSV for different perspectives, datasets for human-robot interaction, that neuromorphic dataset NUAIR. Standardized benchmarks built on these datasets are also crucial for objectively comparing different algorithms. The focus is shifting towards smarter data, rich, varied, well-annotated, and ideally, bias-free.
But standardizing and ensuring the quality of these new datasets is its own challenge.
It is. Data collection, annotation, sharing, and quality control are significant ongoing efforts in the field.
So wrapping this all up, we've covered a lot of ground, from the core AI tech to real-world effectiveness, challenges, ethics, and the future. What's the main takeaway? Are AI-driven, smarter cars leading to safer streets?
Well, it's clear AI represents a massive technological leap in how cars perceive the world, especially pedestrians. We definitely have smarter cars with capabilities far beyond older vehicles.
But the safer streets part is more nuanced.
It is. There's statistical evidence showing these systems, particularly P-AEB, are reducing certain types of pedestrian crashes. That's a positive step. But effectiveness varies, and significant limitations remain, especially in challenging conditions like nighttime or bad weather, and concerning biases persist. Unpredictable human behavior is still a huge hurdle.
So the promise is there, but the full realization requires more work.
Exactly. It needs a multi-pronged approach. Continued technological advancement is crucial, more robust perception, fairer AI algorithms, better prediction models, potentially new sensor types like thermal becoming standard, and usable, explainable AI.
And addressing the ethical side.
Absolutely. Ethical vigilance is key. Clear lines of accountability, strong data privacy protections, thoughtful governance around pre-programmed ethics. Robust, adaptive regulatory oversight is needed to set meaningful performance benchmarks and harmonize standards globally.
And we can't forget the human element.
Never. Driver education about system capabilities and limitations is vital to prevent over-reliance. And ultimately, this requires collaboration between industry, academia, governments, and the public.
Building and maintaining public trust seems fundamental.
It really is. Transparency, fairness, reliability, clear communication, these are essential.
So while AI holds immense promise and has started to make a difference, the journey to truly safe streets for pedestrians requires both relentless innovation and unwavering responsibility.
Perfectly put. The very concept of safety is evolving too, moving towards proactive collision avoidance within a connected ecosystem. This forces us to think differently about risk and responsibility. The ultimate goal has to be protecting all road users, especially the most vulnerable.
Forging a future where technology and responsibility work hand in hand.
That's the hope. Truly safer streets for everyone.
Thank you so much for breaking all of that down for us today. It's been incredibly insightful.
My pleasure. It's a critical topic and it's moving fast.
And thank you, our listener, for joining us on this deep dive into AI and pedestrian safety. We've seen the potential, but also the significant hurdles still ahead. Technology offers powerful tools, but ensuring they translate into real safety for everyone on our streets requires careful development, rigorous testing, ethical consideration, and ongoing vigilance. This deep dive was brought to you by the Be Safe, Be Seen podcast, sponsored by Reflectos, the high-visibility cycling and running gear brand. Here's a final thought for you. Considering everything we've discussed, what do you think is the single most critical factor needed to ensure AI truly leads to safer streets for everyone? Until our next deep dive, stay safe and be seen.